started on collecting data.
I'm excited for you. And I know you have a lot of teammates here, so tell us a little bit about the team that put these cameras on board.
Right, so the cameras were designed and tested at MIT and MIT Lincoln Lab, and so once the camera testing was complete after the course of many months, we shipped the cameras down to Orbital ATK in Dulles, Virginia, where they were integrated onto the spacecraft bus.
So what makes these 4 cameras so awesome that are on board TESS today?
So TESS's 4 cameras are tiny but mighty, is what we like to say, and they're only about 4 inches across, the lenses, and then they can fit in a mailbox basically. But they're so powerful. The lenses on these cameras are these wide-angle lenses that you can have an entire constellation like Orion in the field of view of one of these cameras.
And how far? I understand it's different than Kepler. They're studying stars closer to us. About what range are we looking at?
So TESS is going to look at near and bright stars to ourselves, and so this is stars within the range of 30 to 300 light years or so, whereas Kepler looked at stars that were in the range of 300 to 3,000 light years. And
is there anything else interesting? I think you were talking about the lenses maybe and things like that are really unique for these cameras.
Yeah, so the TESS lenses look in the wavelengths from green to really red, which is optimized to discover small planets around small stars, which tend to be redder. And the sensors for these cameras are very sensitive. So this is much more sensitive than, for example, your camera phone. So the sensitivity you can imagine, an analog here on Earth would be about the amount of light that a moth blocks out when it passes in front of the full moon.
That's awesome.
Yeah.
So can you use these cameras here on Earth?
Yes, so actually in the lab when we were testing the cameras for the first time when we received a prototype, we had it in its test chamber and we blocked the window for the chamber and left just a little pinhole for light to come in, and we were able to have people stand in front of the cameras and take a selfie.
Oh, that's probably the best selfie ever. And I think we also have a shot. You guys went on a roof at MIT?
Yes, so TESS, we took one of the prototype cameras again in a test chamber that simulates the conditions of space, that it's a cold vacuum, and took it up onto the roof of a building at MIT. And MIT in Cambridge has a lot of light pollution, but we were still able to take an image of this field that had all of these stars, and it was this beautiful dense image of all of these beautiful stars, and the images are only going to get better now that we're heading to our orbit.
Right, and I can't wait to see them. So congrats on launch today, and
thank you.
Good luck.
Thank you.
Back to you, Marie.
Thanks, Amanda. TESS will track down exoplanets ranging from Earth-sized to gas giants, orbiting a wide range of stars with different orbital distances. NASA Edge's Blair Allen sat down with TESS project manager Jeff Velosin to understand how to detect planets that are light years away. Blair?
We're here at NASA Goddard Space Flight Center with Jeff Velosin, the project manager for TESS, the Transiting Exoplanet Survey Satellite. Jeff, this is a very exciting mission looking at exoplanets. Tell us, what is the TESS mission?
So it's another mission in NASA's effort to learn more about planets outside our solar system. So it's kind of an evolution, right? When I went to college, there was no such thing as an exoplanet. One had never been found. Nobody thought there'd ever be one found because they're so small compared to the stars that they go around. So when the Kepler mission flew, maybe 10 or 15 years ago, all of a sudden thousands of exoplanets were discovered, that there were these orbiting planets around stars outside the solar system, that some of them were as small as the Earth even. So Kepler was able to find planets, mostly larger ones, and they focused on one area of the sky. So for years they just looked at one area. So we knew that there's now lots of planets, and probably everywhere you look there are lots of planets. So our mission is a survey mission. So the TESS has a survey word in it. And survey is all about, we want to look through the whole sky. So we're not going to just look in one spot. We're going to look all around the sky over a 2-year period and look for planets. We have very sensitive cameras. We're going to look for Earth-like planets that are closer to Earth.
Right.
Now, by being closer to Earth, it allows further follow-up study. Because if you could find planets orbiting stars that aren't that far away, now the James Webb Telescope, with its big, powerful mirror, can say, okay, I know TESS has told me there's a small Earth-like planet around that nearby star. I'm going to go ahead and focus my powerful telescope. And what happens now is when the planet goes in front of the star, you can actually see the light going through the atmosphere, coming to Earth, and then the spectrum of that atmosphere is available. And the spectrum being what parts of the starlight were absorbed by the planet's atmosphere. And that'll tell you, is there carbon dioxide in the atmosphere? Is there oxygen in the atmosphere? So all of a sudden you can learn about an Earth-like planet and what atmosphere it has. So
is TESS then really sort of putting out this map of potential planets for James Webb?
Yeah, exactly. Exactly. So that's where we fit in, right? So Kepler proved that you could find stars almost anywhere you look that have planets around them. Kepler showed that there's a variety of different types of solar systems that we never would have imagined, and that there are Earth-like planets out there. Now, with a very sensitive set of cameras on TESS, we have 4 cameras on the spacecraft that'll look out at a wider swath of the sky, and then every month or two we'll move and look at a different part of the sky. But one thing we're going to focus on is looking straight up. Think of it as a north ecliptic pole, and that's a place where the James Webb Telescope can stare at that spot with the sunlight not getting in the way of the observation. So that's a place they would like to look for exoplanets, because if you're going to look at the atmosphere of one of these exoplanets, you have to stare for quite a long time every time the planet goes in front of the star. So it's great if they have these objects available straight up in the north ecliptic pole or straight down. So that's a lot of our focus. And so the goal is to find them candidates to look at.
And it seems like this is vastly different from Kepler in that it is doing this complete, I don't know, 360 full range. I don't know how to describe it.
Right, yeah, a whole sky survey.
Yeah.
And the great thing about that is, imagine what Kepler was able to find just blew everybody's minds. Planets that might be all diamond, planets that might have totally water surfaces. Imagine what we'll find when we now look all over the place. Kepler looked at one little area and found all that. We can't even begin to think about what are we going to find in the survey over a couple of years. So yeah, that's the exciting part about it. And the other thing is, what we'll find out is how big these planets are. So when you see the light being blocked, all you can tell is the size of the planet compared to the star. You can't tell how heavy it is. And if you can't tell how heavy it is, you really can't tell what it's made of. So what we're going to do is ground telescopes can actually look at those same targets. They look at the planet's effect on the star. So you think about TESS as looking at light being blocked. Well, what the ground telescopes are doing is the star is wiggling a little bit as it's spinning around, because the planets are tugging on it. The heavier the planet, the more it tugs on the star. That wiggle is really small, but those ground telescopes can quantify the wiggle and then tell you how heavy the planet had to be. Wow. So now you have the size of the planet and the heaviness of the planet, and you can get the density and figure out, is it water, is it solid, is it gas?
Earth-like would be fantastic, but if we find, say, a desert planet, what is the likelihood that we can just go ahead, name it Tatooine, and be good to go?
Yeah, there's a lot of people who are looking for, name your favorite sci-fi movie, right? A lot of people are looking for their favorite sci-fi movie planet. But I think we're going to find that there's probably even more diversity than sci-fi writers have ever thought up. And I think that's already what we've seen from Kepler, is that there's some really weird planets out there. So I think that's what we're looking forward to.
TESS will look specifically for planets with the right makeup to support life. NASA's Stephanie Martin has more on how scientists will use the TESS data.
I'm here with Paul Hertz, director of NASA's astrophysics. Now, Paul, can you tell me a little bit about NASA's search for life in the universe and how it's evolved over time?
Well, the first exoplanets, planets around other stars, were discovered with telescopes on the ground. But it took NASA's Kepler Space Telescope to show that almost all the stars in our galaxies are likely to have families of planets around them. And with the Hubble and Spitzer telescopes, we were able to start sampling their atmospheres and learning something about what they're made of. With the TESS satellite, we'll be able to find planets around the nearest stars to the Sun.
That's fascinating. Now, why are we searching for life?
Well, humanity has always wanted to know whether we're alone in the universe. With TESS and the other NASA space telescopes, we can find nearby exoplanets and then study them with large space telescopes like Hubble and the James Webb, look for signs of habitability on those planets or even signs of life in their atmospheres.
Now, you mentioned habitability, and I've heard the term habitable zone. What is a habitable zone, and does that mean that there's no chance that life would exist outside of that habitable zone?
Well, we know that in our own solar system, the Earth is very conducive to life. It's a rocky planet, and it's a very balmy temperature where liquid water can exist. Planets like Mercury are too hot. Planets like Jupiter are both big and gaseous and too cold. So we want to find planets which are rocky and are in the Goldilocks zone of their star. We call those habitable planets. We're looking for those because on those planets we know that life as we know it could exist.
Now, what's next after TESS? What are the next steps to find life?
Well, NASA's next large space telescope will be the James Webb Space Telescope. We'll be launching that in 2020, and it'll be able to study some of the planets discovered by TESS and look for the gases in their atmospheres. Will they have gases like carbon dioxide, methane, oxygen, or water vapor? Gases that on Earth are indicators of life. And after that, we're going to launch the Wide Field Infrared Survey Telescope. It'll have a special instrument on it, a coronagraph, which will be able to let us measure the light directly from a planet without being obscured by the light from the star. That'll let us take the next step in exoplanet studies.
Now, what drives you personally to study these exoplanets?
Well, I think we're all interested in knowing as much as we can about the universe, and whether we're alone in the universe has always been an interesting question. It's really fortunate that today we're at the beginning of that journey. We've only known there were planets around other stars for 25 years, and now we're putting in space the kinds of telescopes that can let us study them in detail. I think that the exciting thing about the TESS mission is after TESS has discovered planets around the brightest stars, you'll be able to go out in your backyard and point to a star in the sky and say, I know there's a planet around that star. I wonder if there's life on it.
That's pretty spectacular. Thank you so much for your time, and we'll go back to you in the studio.
TESS's main goal is to find small planets with bright host stars in our solar neighborhood. This will open the door for scientists to perform detailed investigations of the planets and of their atmospheres. NASA Edge's Chris Gersh met with Stephen Reinhardt of NASA's Goddard Space Flight Center to learn more about the science behind spotting potential Earth-sized planets.
We're here with Stephen Reinhardt, the project scientist for TESS. How you doing, Stephen?
Not too bad.
What's TESS all about?
Well, TESS stands for the Transiting Exoplanet Survey Satellite.
Okay.
And it's NASA's next Explorer mission, being led out of MIT. And it's designed to actually search all of the bright nearby stars, or nearly all of them, looking for signs of planets, exoplanets. In fact, what it's looking for are transits. It's looking for those events where a planet passes in front of its host star, blocking part of the light, and that gives us this little change in the brightness of the star that tells us that a planet is there.
How are you able to detect that transit from millions and millions of miles away? Because when we've seen the Venus transit, when you see that pretty up close with binoculars, you can see it even live, but how can you see something millions of miles away?
Right, well, the Venus transit is a perfect example. Okay. When you watch that, and if you watch a video from some of the other NASA missions, you can see this black spot passing across the face of the sun. Mm-hmm. Well, now imagine that the sun were just farther away. You don't see the spot anymore. You can't resolve it with binoculars or a telescope or anything else that we've got right now. But what you can do is you can see that star gets so very little fainter. Okay. For instance, if you have Jupiter passing in front of our sun, you see about 1% of the light from the star gets blocked by Jupiter. Okay. So if you were watching that star very carefully and were very, very far away, you would see that the light just suddenly drops and then comes back again. Okay. And so that's the signal we're looking for. We're looking for that little drop in brightness, and we're looking for it to happen regularly, right? If you, for instance, have Earth around the sun, once every year, it would pass in front of the star and block that light. So you're looking for this repeated small change in the small dip in the brightness of the star.
So given that, looking at the brightness, I mean, you have to have pretty sensitive cameras to be able to detect that dip.
That's right. So, you know, I said Jupiter's 1%. Earth around the sun is 1/100th of 1%, or 100 parts per million.
Wow.
So what TESS is designed to do, those cameras are designed to be exquisitely sensitive so that we can detect things that are small changes less than 100 parts per million. And really the thing that dominates a lot of the uncertainty are the stars themselves. Stars are not quiet at the tens parts per million level. So you've got this stellar noise, and then you've got the sensitivity of the cameras, but together we should be able to detect small Earth-sized planets around stars like the sun and even smaller than the sun.
Now I understand you're going to be looking at something like 200,000 stars in that 2-year mission. Are you picking out those stars, or are you just kind of going to a region and say, look, we're just going to look for opportunities in a certain region?
So it's a predetermined list, except where it's not. Most of this list is, there's a group of the science team that have worked on a thing called the TIC, the TESS Input Catalog. Okay. And the TIC has about 3 billion stars, if I remember my numbers correctly, in it. Obviously, we're not going to be looking at all those. Right. It's every bright object in the sky down to a certain brightness level. It's huge. But then there's the actual target list. And that's between 100 and 200,000 stars, and these are stars that are specially selected for specific observations with TESS using a 2-minute cadence. So every 2 minutes they measure the brightness of that star.
Okay.
And those are the stars that have the highest likelihood that we'll actually be able to find an Earth-sized planet around them. So stars that are smaller, it's easier to find smaller planets around smaller stars. Stars that are brighter, and so on. In addition to that, there are additional stars that are proposed by members of the general community through the guest investigator program, and that means that we can observe some other stars that were not necessarily viewed as great targets by the science team, but which somebody out in the community says there's a good reason to look at this star, so we will. And in addition to that, we have the full frame images. So every 30 minutes, TESS takes a picture of the entire field of view, which is 24 by 96 degrees.
Wow.
It's huge. And with that, we're going to be able to find a lot more planets. Now, most of those planets are going to be the large planets. They're going to be Jupiter-sized planets and so on. But it's about 10 times as many of those in the full-frame images than the number of planets that we'll find in those postage stamp data, which are really focused on trying to find the smaller planets.
Now, look at our solar system. Our sun is an average star. Are you kind of targeting those type of stars for possible Earth-like planets, or could you have stars that are much bigger than our sun that could potentially have an Earth-like planet?
So, first off, let me say that when we say that our sun is average, we are really wrong. Our sun is actually kind of unusual. It is a sort of average in size, but it's not actually very active compared to most stars.
Oh, wow.
And there's a lot of other stars out there that are very, very different. So a lot of the stars that TESS will observe are what we call the M dwarfs. So these are much smaller than the sun. They're much cooler than the sun. So for instance, the habitable zone, that region around the star where you could have liquid water on the surface of a planet, is much, much smaller than you have around the sun. Those are going to be very good targets for TESS because they're smaller. The larger stars, if you start talking about some of the stars that are a few times bigger than the sun, the problem is that now trying to find a small planet around this big star, it gets really hard. So, imagine that you have a star that's 3 times bigger than the sun, but you have that same planet, then suddenly it's 1/10 of the as easy to detect as it was before. So while we will look at some of those, it's going to be really hard to find the smaller planets around those kinds of stars. But those are important observations to make because we haven't done a lot of observations of those larger stars looking for exoplanets yet because they're hard. And so we really don't know what the population of planets looks like around those kinds of stars.
Final testing of the TESS spacecraft was done right here at Kennedy Space Center. That happened in the Payload Hazardous Servicing Facility. NASA Edge's Franklin Fitzgerald had a chance to see the spacecraft in the clean room and talk with Orbital ATK's Robert Lockwood.